Okay, we're going to have a look at a couple of questions relating to some objects which are orbiting Earth for VCA physics students. On your data sheet that you get for your exam, you'll see that there's a few equations that could be relevant. First one that we have there is Newton's law of universal gravitation, which is this first one here. Newton's law of universal gravitation, or we have the equation for the gravitational field. This bottom one down here is for circular motion, so it's a way of calculating acceleration, circular motion. So if we've got an object which is orbiting a body, whether it be Earth or whatever, the Sun or whatever it might be, any object which is orbiting is going to have an acceleration which is always acting radially inward. So this is where we can relate gravity and acceleration for an object which is orbiting Earth or orbiting the Sun or orbiting another body. So what I'm going to do is actually make these two equations equal to each other and show you how we can derive a couple of useful equations which could come in handy for a cheat sheet. So if we say that for pi squared r over t squared is equal to g m over r squared, firstly what we could do is multiply both sides by r squared. So if I, what am I doing here? Times that by r squared and times this by r squared, that will cancel that down and it will give us an equation of 4 pi squared r cubed all over t squared which is equal to gm. And what we can do with that is have two variants of it. Firstly, I'll just bring this one way up here somewhere, we've got a bit of room. Divide both sides by g. We end up with m, the mass of the central body, is equal to 4 pi squared r cubed over g by the period squared. So that there is an equation that you can use. It's derived, that will allow you to calculate the mass m of the central body. So it could be a question which is something travelling around Earth, orbiting Earth, or it could be something travelling around the Sun, or it could be a moon for another planet, etc. That will allow you to calculate the mass of the central body, providing you know the radius and the period of whatever that satellite is. Now, the other thing that we can do with this is that if we look on the left-hand side, the two things on the left-hand side that can change is r cubed over t squared. So I'm going to do a second derivation here from this first equation. And what I'll do is I'll leave the r cubed over t squared there. And that will be equal to gm. And then from the left hand side there we need to divide by 4, so put the 4 on the bottom and divide by the pi squared on the bottom. This gives us another equation. If we look at this equation here, on the right hand side the mass of the central object won't change. Universal gravitational constant won't change, pi won't change, and 4 won't change. So all of this on the right hand side is a constant. Which then tells us that this ratio of r cubed over t squared will also be a constant for any satellites orbiting a particular body. So it needs to be the same body, but any satellites could be anything like the Moon orbiting Earth, and geostationary satellites orbiting Earth, communication satellites orbiting Earth, space shuttle orbiting Earth, all of those things orbiting Earth. That ratio of r cubed over t squared will be the same. So now we'll go into a couple of questions where we can use these derived equations. So it'd be a good idea to put those onto a cheat sheet that you might be taking into exam, if you can do that. So we'll go into, if the Moon takes 27.3 days to orbit Earth, and the radius of the Moon's orbit is 3.8 by 10 to the 8 metres, find the mass of the Earth. So this is where the first of those derived equations can come in handy. M is equal to 4 pi squared r cubed. Sometimes you'll see a capital R written, sometimes you'll see a lowercase r written. As long as you know it's the radius of orbit, you'll be fine. Divided by g t squared. Okay. Now what we need to do is substitute some values in. So 4, let's substitute 4, yes, times by pi squared, times by the radius. In our case here, the radius is 3.8 by 10 to the power of 8. And that needs to be cubed, divided by g, which is 6.67 by 10 to the negative 11, times by t, which is the period. What I'm going to have to do is actually do a calculation for t. So it tells us that t is equal to 27.3 days. This needs to be in seconds. So that'll equal 27.3 times 24 for days, times 60 for minutes, times by 60 for seconds, which is equal to 2.36 by 10 to the power of 6 seconds. And that will then need to go into this equation down here. And from our equation, that period needs to be squared. Okay. Now, a bit of a trick when you're doing this particular calculation, it's a really good idea to put that whole bottom line into a bracket when you throw it into your calculator. You can calculate it all in one hit if you're careful, or you can just do little bits and pieces at one time. But if you throw that all into a calculator, you will get the answer of 5.84 by 10 to the power of 24 kilograms. Okay. For those of you who are doing VCE, you might notice that that value is different to the one which is written down for the mass of the Earth on the data sheet. Don't expect, if you're asked to calculate the mass of the Earth, that you will get the same value as what's written on the data sheet. They'll specifically ask you to calculate a slightly different value, and that's to make sure you can do the calculation correctly. So the answer to this particular question is 5.84 by 10 to the 24 kilograms. Okay, we'll move on to the next question. This one, if the Moon takes 27.3 days to orbit Earth, with an orbit radius of 3.8 by 10 to the 8 meters. Find the orbital radius and altitude of a geostationary satellite also orbiting Earth. So this comes back to the second of those equations that we derived before, which had r cubed, let me write that cube properly, r cubed over t squared as being a constant. So that was equal to gm over 4 pi squared, which is just a constant. So what we can do with that is we can actually use it as a ratio. Let me see if I can reduce that a little bit. We can reduce all of that. Look at that. How good's that? Now, I'm going to rewrite this equation. So we have two objects here. We've got the radius of the moon, which is equal to, that's the radius of orbit for the moon, 3.8 by 10 to the 8 meters. We have the period for the moon, which we calculated in the last question as being 2.36 by 10 to the 6 seconds. The other thing that we need is, or looking for, is we're looking for the radius of the satellite, which we don't know what that is. Satellite always stays over the same point, so as Earth rotates it stays over the same place. It takes 1 day to get around. We need that in seconds as well, so that will be equal to 1 day by 24 hours by 60 minutes by 60 seconds, which is equal to 8.64 by 10 to the 4 seconds. So now what we do is we apply this to the ratio that we have, where we have the radius of the moon's orbit cubed over the period of the moon's orbit squared is equal to the radius of the satellite's orbit cubed over the radius of the satellite's orbit squared. So what's happening there is, because all of this is a constant, it means that that is constant. So we just apply this ratio per object which is orbiting around Earth. So if we had the moon, we could have had the space shuttle, we could have had whatever. As long as you're looking at the same object, the radius of its orbit cubed divided by the period squared of whatever the object is travelling around Earth will be a constant value. So we can set them equal to each other. We're looking for the radius of the satellite, and I've just noticed what I've drawn wrong there. I'm going to fix this up. Should be the period, shouldn't it? Like so. So now what I'm going to do is multiply both sides by the period of the satellite squared. Cancels that down. That will leave us with the radius of the satellite cubed equal to the radius of the moon cubed times by the period of the satellite squared all over the period of the moon squared, or the next stage of that is the radius of the satellite will be equal to the cube root of the radius of the moon cubed times by the period of the satellite squared, all over the period of the moon squared. And to get a bit more room, I'll see if I can squish this up a bit more. Look at that. Now we can substitute some values into that. So that will be equal to the cube root. That's going to take a little bit of space there. Lots of brackets come in handy here. So the radius of the moon cubed, radius of the moon's orbit cubed, 3.8 by 10 to the 8 cubed, multiplied by the period of the satellite's orbit squared, so that's 8.64 by 10 to the 4 squared. That's all divided by the period of the moon, 2.36 by 10 to the 6 squared. Now be really careful with this when you throw it into the calculator. Keep the brackets there. Make sure you square things that are supposed to be squared. That's a common mistake, is just to forget to square something. If you throw that all in, you'll get a value of 4.2 by 10 to the 7 meters. So that value there is the radius of orbit. For a geostationary satellite. Now the question also asked to find the altitude. So to find the altitude, do this in red down the side here, we need to get the radius of orbit and we take away the radius of the Earth's surface. So that will be equal to 4.2 by 10 to the 7. Take away, and we're told in the question that the radius of Earth was 6.37 by 10 to the power of 6, and that will give us an answer of 3.6 by 10 to the 7 meters. So the two answers that we needed, there was the altitude answer there and the radius of orbit there for a geostationary satellite. So I hope you find those useful. Catch you later.